Hello viewers, welcome back to my channel. So this is the second lecture for the topic diffraction under the chapter Optics of MAKAUT BTech Physics syllabus, paper code page 101 or 201. Apart from MAKAUT BTech students, any first year engineering students of any other universities may also follow these videos to prepare for your engineering physics paper. In this lecture, I will discuss about different types of diffraction, mainly Fresnel and Fraunhofer diffraction and single slit Fraunhofer diffraction and their intensity distribution, and from there we will also derive the conditions for maxima and minima for the intensity distribution in case of Fraunhofer single slit diffraction pattern. Before starting the video, if you have not still subscribed my channel, then do subscribe my channel, and if you are benefited from these videos, then like and share these videos with others. And if you want to join my online theory classes as well as numerical problem solving classes, then you can contact me through the WhatsApp number given in the screen. Also, you can contact me through the Instagram and Facebook page via direct messaging. So let us start the class. So in my previous lecture, I have discussed about what is diffraction and what are the differences between diffraction and interference. So now in this video, we will start with types of diffraction. So mainly there are two types of diffraction. One is called Fraunhofer diffraction and another one is called Fresnel diffraction. Now what is Fraunhofer diffraction? So in case of Fraunhofer diffraction, the source of light and the screen on which the diffraction pattern would be formed are placed such that they are at effectively infinite distance from the diffracting aperture. That means Fraunhofer diffraction এর ক্ষেত্রে যে source of light and the screen যার উপরে আমার diffraction pattern টা created হবে, সেই source of light and the screen both are placed at effectively infinite distance from the diffracting aperture. Now what is effectively infinite distance? How can I place those two things at effectively infinite distance from the diffracting aperture? Normally তো diffracting aperture থেকে effective infinite distance এ যদি আমি source এবং স্ক্রিনকে রাখতে যাই, দ্যাট ইজ নট পসিবল টু অবটেন। তো নর্মালি আমরা যদি ইনফাইনাইটলি ডিস্টেন্সে তো আমরা রাখতে পারি না স্ক্রিনটাকে এবং সোর্সটাকে উইথ রেসপেক্ট টু ডিফ্র্যাক্টিং অ্যাপারচার। তো সেক্ষেত্রে আমাদের কী করতে হবে? উই হ্যাভ টু প্লেস দোজ থিংস অ্যাট ইফেক্টিভলি ইনফাইনাইট ডিস্টেন্স ফ্রম দ্য ডিফ্র্যাক্টিং অ্যাপারচার। তো কীভাবে আমরা ওটাকে পসিবল করতে পারি? সো উই ক্যান মেক দ্য অ্যারেঞ্জমেন্ট বাই প্লেসিং দ্য সোর্স অ্যাট দ্য ফোকাল প্লেন অফ এ কনভেক্স লেন্স অ্যান্ড অলসো দ্য স্ক্রিন উই ক্যান প্লেস ইট on the focal plane of another convex lens. And if we look at this figure, then we can realize what is going on here. Now this is the point source. Suppose this one is the source, point source, and this one is the diffracting aperture, and this one is the screen over which the diffraction pattern would be formed. So what are the condition of Fraunhofer diffraction? We have to place the point source and the screen at an effectively infinite distance from this diffracting aperture. So how can we make it? We can make it by placing the source of the point at the focal plane of a convex lens and also placing the screen at the focal plane of another convex lens. So this one is convex lens 1, this one is convex lens 2. So what are the purposes of placing these two convex lens? As the point source is placed at the focal plane of this convex lens 1, so the light coming out of this point source will fall upon this convex lens 1 as it is placed at the focal plane. Then this convex lens will make all the light beams parallel to each other. So they will be parallel to each other. So if we extend this parallel beam of lights in the backward direction, so they will never meet. That means they will be meeting at infinity. So by this arrangement we made the point source placed at an effectively infinite distance from this diffracting aperture. Similarly, we have to place the screen at an effectively infinite distance with respect to this diffracting aperture. Then we have placed the lens 2, that is convex lens 2. So after passing through this slit or this diffracting aperture, light waves or light rays will be diffracted, and those diffracted rays from this diffracting aperture will be converged by this lens 2 and the diffraction pattern would be formed upon this screen. As the screen is placed at the focal length of this convex lens 2, so all the diffracting patterns would be, or the diffracted lights would be converged to the screen and pattern would be formed on this. These are parallel beams. So these are at effect parallel beam means without this convex lens 2 these beams will never meet at screen, but with the help of this convex lens we make them converge and to meet at the screen to produce diffraction pattern. So the screen is made effectively at infinite distance from this diffracting aperture. So this is the whole procedure to produce Fraunhofer diffraction. So second type of diffraction pattern is called the Fresnel diffraction pattern. So in case of Fresnel diffraction pattern, the source and the screen are at finite distance from the diffracting aperture. That means here no lenses are used. Here this in case of Fresnel diffraction, the point source and the screen are at finite distance from the diffracting aperture, this one. So in case of Fresnel diffraction, no lenses are used. So these are the differences of Fraunhofer diffraction and Fresnel diffraction. Now we will derive the expression for intensity distribution in case of Fraunhofer diffraction from a single slit. আমরা Fraunhofer single slit diffraction pattern এর intensity distribution টা আমরা derive করব এখন. For that case, we consider a slit or diffracting aperture in the form of a slit which have a slit width of A. So this is the slit width. So a parallel beam of monochromatic light of wavelength lambda is incident normally upon this slit which has a slit width of A. So after diffraction from this slit, the diffracted ray would be these ones and the diffraction angle would be this one, theta. Suppose theta be the diffraction angle. Similarly from here also the diffracted, after diffraction the light waves will pass through the slit and after converging through the lens, converging lens, this one, they will produce in a diffraction pattern at screen here. So without any diffraction, the light waves would have met here, but with the effect of diffraction incident, they will produce or they will meet here to produce diffraction pattern on this screen. So here the slit width is A and angle of diffraction is theta. So this is the setup for Fraunhofer diffraction pattern from a single slit. Now we will derive the intensity distribution from a simplified picture as follows. Now this one is the simplified picture of that arrangement. Suppose this is the total slit width A and we take the coordinate such that it is along, the slit width is along z axis. So this direction is z axis. So if we take the midpoint of the slit as origin, then the slit width will, the coordinate of the slit would be from minus a by 2 to plus a by 2. So from minus a by 2 to plus a by 2 would be the coordinate of the slit along z axis. So total slit width would be A. Now as O is the origin, the coordinate of here, coordinate of this is 0. Now we consider an infinitesimal length of a slit dz at a distance z from the origin. So this one is the infinitesimal length of slit with dz which is placed at a distance z from origin. So dz is the infinitesimal length of the slit at a distance z from origin. So one light wave or light beam from this dz will go in this direction and another one light wave will travel almost the same direction from origin. So those two waves will superpose in space and they will form a diffraction pattern at suppose the point P. So now we have to calculate the path difference between these two waves. So wave 1 and wave 2. So as O is the origin, the distance from P, the distance from O to origin to P, suppose OP is, suppose we denote as R. Now we have to calculate the distance from dz to P. For that we draw a perpendicular from here, from dz to OP here, and the diffraction angle, as the diffraction angle is theta, so this diffraction angle would be this one. So that means if we enlarge the figure, it will be, this one is dz, this angle would be theta and this distance is R, this distance is z, this extra distance value would be, as this one is 90 degree and this one is theta, this extra distance would be z into sin theta. So the path difference or optical path difference from OP to dz to P would be, suppose we take it as rho, and so path difference would be r minus z sin theta, which is equals to rho. And from that path difference, we can calculate the phase difference, as I have discussed in my previous lecture of diffraction. The path phase difference would be 2 pi by lambda times rho. So that would be 2 pi by lambda into r minus z of sin theta. So this is the phase difference due to the path difference. So the phase difference between two waves at P would be this one. Now if we consider the waves are plane waves, so the electric field at P due to that dz element or dz length of slit would be proportional to dz into e to the power I omega t minus 2 pi rho by lambda. As we have considered plane waves, so we can take the form of the plane wave as e to the power of I omega t. Omega t is the instantaneous phase at time t minus the phase difference due to path difference, that is 2 pi into rho, this one, by lambda. So we can take it in the exponential form for the plane waves. The electric field due to dz at P, which is denoted as d, that would be proportional to this element dz, infinitesimal length of the slit with dz, and also it will consist of a plane wavefront, that is e to the power I omega t minus 2 pi rho by lambda. Now if we remove this proportionality sign, then we can put a proportionality constant, that is k. So d would be k into dz e to the power I omega t minus 2 pi rho by lambda. Or if we put the value of rho here, that is r minus z sin theta, if we put the value, the electric field dE would be k dz into e to the power of I omega t minus 2 pi by lambda into r minus z sin theta, or we get dE equals to k dz into, we separate the z term with the non-z term, so e to the power I omega t minus 2 pi r by lambda into e to the power I 2 pi z sin theta divided by lambda. So this is the expression for dE, that is electric field due to dz at P. Now this is the electric field due to dz at P. Now if we want to find out the total electric field at P due to the full slit of width A, then what we have to do, we have to integrate the expression dE. So the resultant field at P would be E equals to integration of d from minus a by 2 limit to a by 2, or we put the value, so we get integration of minus a by 2 to a by 2 k dz, this form, k into non-z term is this one, so e to the power I omega t minus 2 pi r by lambda into z term is e to the power I 2 pi z sin theta divided by lambda into dz. So we have to perform this integration. So we take the non-z term outside the integral form, that is k into e to the power I omega t minus 2 pi r by lambda into integration minus a by 2 to a by 2 e to the power I into 2 pi z sin theta by lambda dz. So we integrate it and put the limit. So this term remains same, this k e to the power I omega t minus 2 pi r by lambda. In third bracket it would be e to the power, this integration would be in the form of e to the power mx dx. That means e to the power m by e to the power mx divided by m, and then we have to put the limit minus a by 2 to plus a by 2. So here integration is over z. So we have, after integration we will get one by this whole term except z, that is 1 by I 2 pi z 2 pi into sin theta by lambda into, in bracket it would be e to the power I into 2 pi z sin theta by lambda. We have to put the limit minus a by 2 to plus a by 2, or after putting the limit we get this term will be same with our I omega t minus 2 pi r by lambda into 1 divided by I into 2 pi sin theta by lambda into, after putting the limit it would be e to the power of, we put the limit a by 2 in place of z, so it would be e to the power of I into 2 pi a sin theta by lambda minus e to the power of minus I, 2 pi and a by 2 will cancel out, so it would be only just e to the power I pi a sin theta by lambda, and second term would be e to the power minus I pi a sin theta by lambda. Now we take pi a sin theta by lambda equals to alpha to make this expression simplified. So pi a sin theta by lambda equals to alpha. So if we put it here, it will be k into, this term will be same, I omega t minus 2 pi r by lambda into 1 by, it would be 2i into pi a sin into, if we multiply both numerator denominator with a, then we get numerator is a, in denominator it will be 2 pi a sin theta by lambda, that means 2i into a sin theta by lambda is alpha. Here we have used the trick that we have multiplied both numerator and denominator with a. So numerator it would be a, denominator it would be I into 2 pi a sin theta by lambda. Again we have taken pi a sin theta by lambda equals to alpha. So denominator it would be 2i into alpha. So, and this term, third bracketed term would be e to the power I alpha minus e to the power minus I alpha. So this we can write it as in the cosine and sine form, and finally we get it as 2i sine alpha. Now we put it here, so we will get k e to the power I omega t minus 2 pi r by lambda a by 2i alpha into 2i sin alpha. So this will cancel out 2i and 2i. So finally we get, that is electric field total equals to E after integration e to the power k into a, so this k into this a into sin alpha into sin alpha divided by alpha into e to the power I omega t minus 2 pi r by lambda. So this is the final expression for electric field at screen. So we know that to find out the intensity from this electric field, we can obtain the intensity as E into its complex conjugate. So the intensity would be this one into its complex conjugate, means k square s square into sin square alpha by alpha square into this one, this expression and its complex conjugate will make it 1. So we obtain the final expression for intensity, expression of intensity distribution for single slit diffraction pattern, single slit Fraunhofer diffraction as I equals to, we take it as I0, this constant term, so I equals to I0 sin square alpha by alpha square. So this is the expression for single slit Fraunhofer diffraction intensity. So now from this intensity distribution, we have to find out the position of maxima and minima on the screen. So this is the intensity distribution. This equation 2 is intensity distribution for Fraunhofer diffraction pattern. So from to find the maximum intensity and minimum intensity condition, that means to find I max and I min, we have to differentiate this expression with respect to alpha, and we have to find out d alpha equals to 0. From there we have to calculate, or we have to find out the conditions for intensity max and intensity minimum. So d alpha 0, that means if we differentiate this expression with respect to alpha, we will get I0 into, by division method, if we differentiate it, it will be alpha to the power 4, that is alpha square, into differentiation of sin square alpha would be 2 sin alpha cos alpha minus sin square alpha into differentiation of alpha square would be 2 alpha. So this should be 0. We take common 2 alpha into sin alpha, in bracket it would be alpha cos alpha minus sin alpha, that is 0. Or from here we get two conditions. The condition one is either sin of alpha is 0, or second condition would be alpha cos alpha would be sin alpha, or alpha equals to tan alpha. So these two conditions, from these two conditions we can find out the positions of maxima and minima. So now let us take case 1, that is sin alpha equals to 0. Here sin alpha equals to 0 means alpha would be plus minus m pi, where m starts from 0, 1, 2, 3 and so on, and alpha, we have taken alpha as pi a sin theta by lambda in our previous step. But now if m0, alpha becomes 0, alpha becomes 0 means this expression becomes 0. So for m0, alpha 0 means pi a sin theta by lambda equals to 0, which is equals to alpha. So from the intensity distribution graph here we get both alpha 0 means for m equals to 0, alpha 0 means in this intensity distribution numerator term is 0, also denominator term is also 0. So as a result of that, what we get, I seems to be infinity, but infinite intensity is not possible. So what we have to consider here, we have to take the limit, that limit alpha tends to 0, and we have to find out the value of sin alpha square by alpha square. So here in case of m0, for m0 alpha becomes 0 as well as sin alpha becomes 0. So for intensity distribution we have to take I equals to I0 limit alpha tends to 0 sin square alpha by alpha square. So here is what trick we have to do, we have to take the limit, otherwise intensity is becoming infinity, which is impossible. So for alpha tends to 0 we have to take the limit, so that limit alpha tends to 0 sin square alpha by alpha square value becomes 1 as limit alpha tends to 0 sin alpha by alpha is 1. Sin alpha, limit alpha tends to 0 sin alpha by alpha is 1. So this total term would be 1. So I becomes I0 for m equals to 0. I becomes I0 means this is the principal maximum position. So for condition sin alpha equals to 0 and m equals to 0, we get position of principal max. Where I becomes equals to I0. So for the condition m equals to 0, we obtain the position of principal maxima. Now from this condition alpha equals to plus minus m pi, when m not equals to 0 means it starts from 1 to infinity. So for m other than 0, the condition would be alpha becomes 0, that is pi a sin theta by lambda. So alpha becomes this one. So for m not equal to 0, that is 1, 2, 3, starting from 1, the value of alpha is this one. This is non-zero, but value of sin alpha becomes 0. So the intensity distribution I becomes I0 into, in numerator term, that is sin square alpha, denominator alpha square. So this one is non-zero, but this one is 0. So these are for values m starting from 1, 2 and 3 and so on, we get I becomes 0, that means position of minimum. So the difference from m equals to 0 to non-zero is, for m equals to 0, both the numerator sin alpha and denominator alpha becomes 0. But in case of m not equal to 0, just numerator becomes 0, denominator becomes non-zero. These are the two differences. So from here we get the value of sin theta, that alpha equals to plus minus m pi, means pi a sin theta by lambda is plus minus m pi, where m 1, 2, 3 so on. So from here we get pi cancels out. So sin theta becomes plus minus m lambda by a. So this is the position of minimum intensity. So this is the minimum intensity condition. So first we got the principal max condition, second we obtain the minimum intensity condition. Next we will consider the second condition, which we obtain as alpha equals to tan alpha. Alpha equals to tan alpha. These type of equations are called as transcendental equation. And these type of transcendental equations can be solved graphically. Now for that case we have to take two equations as y equals to, one is y equals to alpha and another one is y equals to tan alpha. Then we have to plot these two equations, and from there the intercepts will be the solution. So from these two equations, after plotting the intercepts of these two graphs are the solutions. Now y equals to alpha graph is straight line graph passing through origin, and second is y equals to tan alpha graph. So here these are the alpha versus tan alpha graph. So first we have plotted the y equals to alpha graph, which is passing through this origin O. So this one is y equals to alpha graph. This is passing through origin O. And second one, y equals to tan alpha graphs are these ones. This one, this one, this one. These are all y equals to tan alpha graph. So y equals to tan alpha means, so as tan alpha has the limit minus infinity to infinity, so they will reach at infinity here, minus infinity to plus infinity. And for alpha values of 0, pi, 2 pi, 3 pi, and again similarly in the negative direction minus pi, minus 2 pi, minus 3 pi, for those alpha values the y would be 0. So these are the points which is passing through y0. And similarly for y equals to pi by 2, 3 pi by 2, 5 pi by 2, and similarly in the negative direction minus pi by 2 to minus 2, 3 pi by 2, minus pi by 2, they will be along infinity. So now if we find out the intercepts of these two graphs, we will obtain the solution of this transcendental equation. So from here we can say that y equals to alpha graph and y equals to tan alpha graphs intercepts at firstly at origin, secondly at this point, thirdly this point here, and similarly in the negative direction as here, here and here. So all these points are the solutions of this transcendental equation. So all these intercepts will have some alpha values. So here first intercept is alpha when alpha equals to 0. So here it is alpha 0. Second intercept is here. So here it is alpha equals to 1.43 pi. Similarly third intercept is alpha equals to 2.46 pi, and similarly this one. So along negative axis also, negative direction also, this would be alpha equals to minus 1.43 pi. This would be alpha value would be alpha equals to minus 2.46 pi, and so on. So all these values of alpha, that is alpha 0, alpha 1.45 to plus 2.45 or alpha minus 1.45 minus 2.45, all these are positions of principal, all these are positions of secondary maxima. So alpha position of secondary maxima can be found for alpha values 0, plus minus 1.43 pi, plus minus 2.46 pi, plus minus 3.47 pi, etc. So if we put the value of alpha here, we will get the sin theta value. That means pi a sin theta by lambda. Suppose this one is for plus minus 1.43 pi. Now Why I have not taken this 0, I will come it later. So suppose pi a sin theta by lambda equals to plus minus 1.435. So pi cancels out, we get sin theta equals to plus minus 1.43 lambda by a. Similarly, we take 2.465, we will get sin theta value would be plus minus 2.46 lambda by a. Similarly, plus minus 3.47 lambda by a. So these all these are positions of secondary maxima. Position of secondary maxima. Now, what I have skipped, and I told that I will comment later, that when alpha equals to 0, alpha 0 means what? As I have already discussed previously, alpha 0 means principal max. So here, to find secondary max, we cannot take alpha value 0. We have to start from this value 1.435. So apart from 0, all other alpha values are the positions of secondary max. So all these are for sin theta values are the position of secondary max. Now what we will obtain from the intensity distribution on screen. So this is the intensity distribution graph. This is the intensity distribution where we can see this one is the value of I0, that means this one is principal max. Means for here m value is 0 or sin alpha value and alpha both are 0. So these are principal max, and these are the positions of minima that we have already found out in previously. Positions of means the values of sin theta for this minimum position, and these one are the secondary max that currently we have derived, that this for this value alpha value is plus minus 1.40, 2.46, etc. So this one is principal max position condition, and these one are the secondary max, and these are the minimum position, and the intensity on the screen would be similar to this graph, this figure or this picture. So this one is central max, this one is first secondary max, second secondary max, third, and these are the minima positions on the screen. So this is the total intensity distribution, and from the intensity distribution we obtain the positions of different maximum and minimum intensities. Now we will discuss a special case. What happens when the slit of the width is made narrower, and what is the effect of this on intensity pattern on screen? So earlier we have derived that position of minimum is given by sin theta equals to plus minus m lambda by a. Now you can see that when the slit with a is made narrower, that means a becomes less, then sin theta becomes high. So whenever we are making narrower slit width, then sin theta value or the position of minima would be broadened. That means sin theta value high means minimum position would be broadened. So in case of this figure, these are the positions of minima. So this position of minima would be broadened. That means this will go along more this direction, this will go more this direction. So as a result of that, if we decrease a, the position minima would be at higher theta values. So the principal max intensity will be broadened. So this will be more broad, this will be broader, more broader, and finally it will take the whole screen as principal max, or principal max will cover the whole screen or the full screen when we reach the terminal position of lowest slit width. So what will happen if we decrease the slit width? The principal max will be broader, and gradually it will take the full screen. And when lambda equals to a and theta becomes 90 degree, for a sin theta equals to m plus minus m lambda by a. Now when lambda equals to a, that means wavelength is exactly equal to the slit width. Then sin theta becomes plus minus m. For first order m equals to 1, theta would be 90 degree. Theta 90 degree means the full screen will be covered by the central maxima. So this is the total case of Fraunhofer first order diffraction and their different conditions for maximum and minimum intensity. So in MAKAUT June 2024 semester question paper, a full 15 marks question came as what are the diffraction light that I have discussed in my previous video of diffraction, and explain the difference between the interference and diffraction. That also I have discussed in my previous video of diffraction. The link of this previous video I will provide it in the description section of today's video. Second question, can derive the expression of intensity at a point for Fraunhofer diffraction due to single slit. I have discussed in today's class. Third question came, find the conditions of central maxima, minima and secondary maxima for a single slit Fraunhofer diffraction. The third question came as, find out the conditions for central max, secondary minima and secondary maxima for a single slit Fraunhofer diffraction. That just I have discussed. So all this full question can be solved by today's lecture. So তোমরা দেখতে পাচ্ছ একটা পুরো ফুল 15 মার্কস কোশ্চেন এই টুডেজ আজকের লেকচার থেকে একটা পুরো 15 মার্কস কোশ্চেন এসেছিল MAKAUT জুন 2024 এর যে সেমিস্টার পেপারে, ফিজিক্স সেমিস্টার পেপার। আর এই থিওরিক লেকচার্সের সাথে সাথে নিউমেরিক্যাল প্রবলেমসও তোমাদের সলভ করতে হবে। ইন অ্যাডিশন টু দিস থিওরি লেকচার্স ইউ হ্যাভ টু অলসো সলভ দ্য নিউমেরিক্যাল প্রবলেমস। ফর theory and also numerical problem solving classes, you may join my online classes. So this is the end of today's class. See you in the next class in a new video. Till then, bye.